So, hello everybody. My name is Stefanello. I've been involved in AI research in the early 80s. And then I had a career managing big programs in space and aeronautics. And I've been very frequently involved into certifications of critical software. For instance, my teams help Aerospatiale to certify the S320 piloting software. And obviously, I've followed all the research in AI all along those years and realized in the early 2010 that the AIs as they are today are not certifiable. And I'm now in the process to try to create a foundation dedicated, which will be an international organism dedicated to AI safety. So if you want, I will take the lead on the screen.
Yes, please.
I hope it will work.
Fion, does he have permission to share his screen?
Does it work? Do you have my screen?
Not yet.
Not yet. Sorry, because it's supposed to work. So let's try it again. Okay, this, I think. Do you have it now?
Yes.
Okay. So, I don't need that. Sorry. Okay, so here are the two questions that have been asked by Vinciane and Sophie. Sorry for the ones who already know what is AI in depth, because you will not learn anything. But my goal for here is to help people who don't have a technical knowledge of AIs to build their own representation of what are really AIs and how does this work, and of course, where are we in terms of control. So I start my chronometer for those 20 minutes. So in the classical world, classical digital world, when you want to make some calculations, you have a representation from the world. You start from a representation of the world. And from this representation, you build a program, which is a set of instructions. And with some input data, then with this program, you got the output data. And at the very end, it's the human, the man who have, and women who have written the logic, the rules, the program. The code is readable, testable, and so on. And it has a deterministic behavior. Same input, same output. In the world of modern AIs, it's totally different. You don't have any representation of the world. In fact, you have some input data which correspond to some output data. And it's the computer, it's the architecture that we have set up, which creates, in some sort of way, the program. So we correlate the input and output data, and it creates the program. It's the training which creates the program, the so-called program. It's important to note that, in fact, this way of thinking is a very ancient one. When the old peasants were looking at the clouds, at the way the chickens behave, and so on, and were able to determine what will be the weather of tomorrow, it was the same kind of approach, trying to correlate data and then create an output. By the way, the scientific process very often start in the same way. We try to understand why the outputs are concerning the output that we've put in. So it's not something totally weird for us. But this is very important to figure out this big difference, because the goals, the data, the tests are very important in this world of AIs. It's not only the program, the code. And of course, you understand that if the data are not totally sane, or if they drift and so on, the behavior of the machine will drift also. And first remark, but we'll come back on that, is that what we call today alignment of AIs, it's in fact ex post practical guardrails, but not at all formal guarantees over the behavior of those AIs. So perhaps it's important to excuse, it will be the only mathematical thing in my presentation, but to really figure out what are those neuronal AIs. So a neuron, what is it? If you look at this sigma in the center of the screen, this is the neuron. This is the neuron of one layer of neurons, and it depends on all the XI neurons of the previous layer of neurons. So here on the left, you have the previous layer on the, of neurons. And we make some calculations, very simple, by the way, because the F function here generally is very simple. And we take all the outputs of the previous neurons from the previous layers. We multiply them by what we call parameters. It's the W, I1, I2, IIN. We add a bias, the B, and then we calculate the output. This is a neuron in a neural AI architecture, and that's the way, from a calculating point of view, that's the way it works. So let's take an example which was the first example of an AI which worked, and which is still be used by the US Postal. The US Postal wanted to recognize the various numbers that people are writing on letters and parcels. And the classical approach with the representation of the world that I was explaining never worked very well. People try to approach those numbers through vectors and so on, but it never worked very well. And at that time, Jan LeCun was an obscure researcher in Canada, but he had already worked on neuronal system, and he had, if I may say so, in his pocket, a 10-layer neuronal network. And he said to himself, "Oh, let's try if it works." So he took a representation of 28 by 28 pixels, so it's 84 values, which are then just black or white. And as an input of his neuronal system, he put those 784 values. So my drawing is here is not correct, because on the left we should have not only 10 neurons, but 784. So let's imagine that there are just 784 values on the left. And he rearranged his neuronal network so that at the very end, he had only 10 neurons, which will be the 0, 1, 2, and so on and so on. And then he started the learning process. The learning process was very simple. It was to put all the USPS database of the various numbers that they've seen on their letters and parcels. It was thousands and thousands if not millions of examples. Again, input and output, because for each input, there was the corresponding output saying this is a 7, this is a 4, this we don't know, and so on and so on. And through this learning process, he set up the parameters, because in fact the parameters are fine-tuned by the learning process. The program comes out of the deep learning through the self-adjustment of internal parameters. It's the WIN of my previous slide. And how do we do that? We do that through backpropagation, meaning that during the learning process, when the machine doesn't recognize a 2 in some sort of way, we say to it, no, it's not a 2, this is not a 2, this is a 3. And then we backward this information all through the neuronal network. And the machine adjusts with this function of backpropagation, adjusts the various parameters in a tiny way for each and every example. But with the big amount of learning process that we do, at the very end, it fine-tunes all the parameters, and that's magic. It worked at the very end. Even Jan Leuken was surprised, but it worked very, very well, and it's still used by US Postal. One remark here, at the very beginning of this story, neuronal AIs have been made more by geeks and pirates than by proper mathematicians or computer scientists. And at the early days, those guys who were inventing AIs were not very well seen by the, let's say, the academic computer science collectivity, because it was test and try, and they try and they built all that in some sort of way without knowing how it works really. Second very important thing is that, and how the LLMs works, is that we've turned language into vectors. So take the 50,000 words of English, take all the Washington Post journals during 30 years, and measure the distance between each and every word. And then you end with 50,000 matrix by 50,000. Then you rearrange vectors so that words with similar context end up near each other. So you reduce this dimensional space to 300. And you end up with a space vector. So it's very difficult to figure out in our mind, but let's say for mathematicians, it's very easy to calculate vectors. And for instance, king is a 300 set of numbers, and queen and everything and so on. So this, at the very end, means that we've got a vectorized and calculable version of the language. Note that everything started with English, and that even in DeepSeek, the inner core of DeepSeek is English. It's not Chinese. It has been Chinesized after, if I may say so. So with this representation, the language become calculable. If you take the vector king minus the vector man plus the vector woman, you end up with a vector which is very, very, very close to the vector queen, which is obvious because king minus man plus woman is queen. And by the way, the difference between king and queen end up to be the same difference than the difference between nephew and niece, between son and daughter, and so on and so on. No, so we end up with a really calculable version of the language. with context. For instance, the vector house is near to the vector flat. We have also the context of verbs, nouns, adjectives, and so on. You can make some sorting on those vectors very easily, and this is very important. Then you can infer statistically what could be or what will be the next word in a phrase. If I have I fall from my, so that these are 4 vectors, then the machine can very easily infer that after I fall from my, there will come, it might come chair, car, my tree, and so on, but it will not be I fall from my Baba Rum, for instance. You see? So, and it's such a vectorial representation of language which allows LLMs to understand your prompts and to answer to your prompts. Understand here means that they compute useful this geometric structure of a text that we've built. This has been built in the early 2010. But again, understand here doesn't mean human comprehension. And for this seminar, I think it's very important to understand that. It's like a calculator for language, if I may say so. Of course, model LLMs don't use a single fixed vector per word. They use also, they build some contextual embedding. That's what we call attention, because in riverbank, bank is not the same than in bank loan and so on. LLM speaks words in subword tokens, but at the very end, this is the way it works. I think it's important here to stop a little bit on what is intelligence, because we've called them artificial intelligence.
Eric, sorry,
Yes?
just as you get into this bit, just to give you a note that there's 5 minutes remaining.
Okay, so if you consider that intelligence is the way to solve problems, there are many sorts of intelligence. When bacteria took other bacteria to create mitochondria, it was a kind of intelligence, just a biochemical intelligence, but that's intelligence. A colony of ants is intelligence, a dog, and so on. And then there's our intelligence. So I would like to propose you a different definition of artificial intelligence, because from a strict mathematical standpoint, we should call them massive correlator of vectorized data. This is what are today artificial intelligences. Why does it work? Because it's behind this, there is colossal computer power. I will skip that because time is running. And let's go now on what goes wrong today. We observe lots of failure modes, hallucinations, spec gaming, jailbreaks, bias and sycophancy, data leakage, non-stationarity in the way AI behaves, deceptions under pressure, manipulation of AIs, goal guarding, and self-preservation proxies, which is sometimes very frightening, and so on. AIs are totally today uncontrollable. They have high capabilities, but we don't have any guarantees on the way they behave and the way they work. That's important to look at. So I've only 3 to 4 minutes. Here you have two examples. One of hallucination, which has been really studied, another one of bias and sycophancy. Let's skip to the conclusions, and of course there will be a lot of questions at the very end. I'm used to make this presentation during a 2 or 3 hours conference, so 20 minutes, it's a bit difficult for me. The big data led to the victory of the connectionists, the pirates and the geeks I was talking about. An AI does not reason, it does not model, it correlates massive data sets through huge graph of self-adjusting parameters. Mathematically, it's correlation under minimization of error function. An AI self-programs through the learning process. There is no algorithm in an AI, and an AI is a black box. And one very important point is that we don't have the math today to understand their behavior. An AI does not create knowledge. It infers from data. It may change with AGIs in the future. Even that the math we've put inside the AIs, I was talking to you about the functions, are very simple. So we use the weight of each neuron. I've explained that. This is the victory of brute force over the historical symbolic approach of the early AIs, expert systems. We do not know what's inside, nor exactly how they behave. They are non-deterministic and non-certifiable. We have no control at all on these machines, and we are just trying to patch them ex post with what we so-called name as alignment, but it doesn't guarantee anything. And let's finish with a conclusion, which are not mine, but some of Stéphane Dehaene, a neurobiologist. Artificial networks are very good at modeling the early stage of vision, of reading and processing language. But today, we kept the upper hand in our ability to learn from a very small number of examples, as child does during their infancy, which is really amazing the way child learn from the world in which they live. And AIs are very bad at discover abstract, compact representation of knowledge. In other words, they are very bad at modeling the world. And if someday new architectures of AIs will be able of that, then we will be very close of what we call AGI, artificial general intelligence. And remember that our brain is only a 20-watt machine.
Eric, thank you very much. People are clapping.